Find the work done by the Coulomb force between two charges in moving one of the charges from an initial position at point A to a final position at point B on a line connecting the two charges. Well, for this example, let's begin with a coordinate system that is centered on one of the charges. For this coordinate system, the horizontal axis will refer to the line on which the charges lie, and we will position the first charge, the charge at which this coordinate system is centered. We will position this first charge at the origin, and we will label this charge Q1. So this coordinate system is from Q1's frame of reference. Let's now position a second charge on this line. The second charge, which I will label as Q2, the second charge is located at point A relative to the first charge. So point A, I will signify its location with a position vector, which I will label as R sub A. Being two charges, there will be a Coulomb force that exists between them. For this example, let's suppose that both charges are positively charged. That means that there will be a Coulomb force of repulsion on each charge due to the fact that they are point charges. The Coulomb force of repulsion is equal in magnitude, but opposite in direction on each charge. For now, we're going to focus on charge 2 since we are keeping charge 1 fixed at the origin of its own coordinate system. Being two charges that are exerting Coulomb forces on each other, Newton's third law says that the force is equal in magnitude on each charge, but opposite in direction. We're focusing on charge 2. So the Coulomb force of repulsion on charge 2 due to charge 1 is given by Coulomb's constant times the product of the charges divided by the distance between the charges squared. Let's now look at charge 2 at another point on this line. Charge 2 is located at point B along the line connecting these two charges. At point B, since point B is farther away than point A, the Coulomb force of repulsion on charge 2 will be smaller. Let's use a position vector to refer to the position of charge 2 at point B. From this sketch, you could see that there is a displacement between points A and B. You may remember that if there is a component of a force in the direction of displacement, then the force does work on an object. And in fact, we could define work as the line integral of a force acting on an object in moving the object between 2 points, in this case between points A and B. One version of the dot product between two vectors allows us to represent the dot product as being equal to the product of the magnitudes of the two vectors, in this case the two vectors being the Coulomb force on charge 2 and the displacement vector, times the cosine of the angle between those two vectors. Since the Coulomb force acting on charge 2 is in the same direction as the displacement of charge 2, we know that the angle between those two vectors is 0 degrees. And if the angle is 0 degrees, then the cosine of the angle is 1. This allows us to write that the work done in moving charge 2 from point A to point B is equal to the magnitude of the Coulomb force between the two charges, which is k q1 times q2 over the distance between them squared, times the magnitude of an infinitesimal displacement between points A and B. The Coulomb constant and the product of the charges can come outside of the integral, leaving us with an integral from A to B of 1 over r dr. We can now evaluate this integral to be minus k times the product of the charges times 1 over r evaluated from our initial position to our final position along the r-axis. The result ends up being minus k q1 q2 times 1 over the final position along the r-axis minus 1 over the initial position along the r-axis. So here is the expression of the work done by the Coulomb force in separating two charges that are initially at a certain distance r of A, ending up at a final distance r of B on a line connecting the two charges. What we are really interested in is the fact that the Coulomb force is a conservative force. It doesn't take too much effort to show that the work done by the Coulomb force in moving charge 2 relative to charge 1 is a conservative force. This is because a conservative force has the following properties. The work done by a conservative force can be expressed as a function, as a scalar function only. So let's write that down. The work done by a conservative force can be expressed as a function of position only. Notice what we have here. We have an expression for work, and that expression for work involves a final position of our object and an initial position of our object. Everything else is a constant. So here, work is expressed as a function of position only. Another property of a conservative force is, in moving an object between 2 points, the work done by a conservative force is independent of path. So what does that mean? What that means is, if you take an object and you start that object at a point A, and you want that object to end up at another point B, it doesn't matter how you get from point A to point B. You could go from point A to point B along a circuitous path. You can go from point A to point B along a straight line path. You could go from point A to point B along a meandering path that takes its time. The only thing that matters is where you start and where you end. Regardless of which path you take to get from point A to point B, the work done by a conservative force on that object is the same. Now that makes sense because as you could see here for the work done by the Coulomb force, it's a function of relative position, and you know what? The only thing in this function is the final position of the object and the initial position of the object. Notice how this function has no indication of how we got from point A to point B. The only thing that matters is where we started and where we ended, starting at the initial position A and ending at the final position B. Another property of a conservative force is that the work done by a conservative force in moving an object in a complete loop is 0. Let's write that down. The work done by a conservative force in moving an object in a complete loop is 0. Well, what does that look like for this? Let's again take 2 points, A and B. Let's say we start off at point A, end up at point B. Or at least point B is an intermediate stopping point on our journey. So this might be a trip from home to work. But at some point in the day, we got to return back home. So going from work back home, we end up leaving point B and returning back to point A. So there will be a certain amount of work done in moving that object from point B to point A. Well, a property of the work done by a conservative force is that the work done in moving an object from point A to point B plus the work done in moving the object from point B back to point A is equal to 0. What that means for this picture is, let's just put some arbitrary numbers here. If the work done in moving this object from A to B involved 100 joules of work, if this represents a conservative force, then the work done from B to A must be equal to minus 100 joules of work. So we can ask the question now, does the work done by Coulomb force have this property? Does it have the property that when that charge 2 moves in a complete loop, the total work done is 0? Well, let's look at it. We had shown that the work done is equal to minus K times the product of the charges, Q1 and Q2, times 1 over the final distance minus 1 over the initial distance. Let's call this the work done from A to B. Again, this term here is the final position, and this term is the initial position. Well, let's get an expression for the work done from B back to A. The work done from B back to A is going to be, it's still going to be minus K Q1 Q2. However, what's inside the parentheses swap. So our new final position is point A. Our new initial position is point B. Because for the second leg of this journey, we started at B and we ended right up back at A. Let's sum these two quantities now. The work from A to B plus the work from B to A is minus K Q1 Q2 times 1 over the point B minus 1 over the distance at point A minus K Q1 Q2 times 1 over the distance at point A minus 1 over the distance at point B. Let's factor out the constants K, Q1, Q2, and the minus sign from both expressions. This leaves us with a 1 over the distance at point B minus 1 over the distance at point A plus 1 over the distance at point A minus 1 over the distance at point B. Notice everything cancels out. This means that the work done by the Coulomb force in moving charge 2 in a complete loop from point A to point B back to point A is equal to 0. The Coulomb force has these properties of a conservative force, that the work done can be expressed as a function of position only, that in moving one of the charges between 2 points, the work done was independent of path. And finally, in moving the charge in a complete loop, the work done, total work done, is 0. Why is this important? This is important because it allows us to say that a conservative force stores energy, and we call that energy potential energy. Let's write that down. A conservative force stores energy in the form of potential energy. What that means is whatever amount of work that a conservative force does, we're able to recover that amount of work in the form of energy later. Potential energy is really defined as a change of potential energy between 2 points. The potential energy at some point B as a function of relative position minus the potential energy at some point A as a function of relative position is equal to minus the work done by a conservative force in moving an object from A to B. For our Coulomb force, the work done in moving the object from A to B was equal to minus K times the product of the charges times 1 over the final position minus 1 over the initial position. Well, this minus times a minus is a plus. And we get that the change of potential energy as a function of position is equal to the Coulomb constant times the product of the two charges divided by the final position minus the Coulomb constant, product of the two charges, divided by the initial position. And over here, let me just put a subscript B and a subscript A. Well, notice what we have here. We have an expression where the left term, the first term on each side of the equality, corresponds to a final position. And the right term on each side of the equality corresponds to an initial position. In other words, the potential energy at point B, we could say that that is equal to the Coulomb constant times the product of the two charges divided by the final distance. And the potential energy at point A, we could define, and in fact, this is a definition, we could define as being K times the product of the two charges divided by that initial distance. Well, notice the form of this at either point is the same. Since the form is the same, let's go ahead and define the electric potential energy as being equal to the Coulomb constant times the product of the charges divided by the separation distance between the two charges. We're going to take this to be our operating definition. With this operating definition, though, there is one thing that remains assumed. That thing that with this definition, we have to bear in mind an important convention. In order to apply this definition, we're going to hold the convention that we will take the potential energy when we are infinitely far away. So when the two charges are separated by an infinite distance, we're going to define the potential energy between those two charges to be zero. If we hold this definition that the potential energy of two charges separated by an infinite distance is zero, then our definition of potential energy will work, where potential energy is a function of position only, based off of this separation distance between the two charges.